அந்த சவுண்ட் வந்து யாரும் கொடுத்துறாங்கப்பா பார்த்து.
Hello.
Good evening, sir.
Good evening to all of you. Am I audible?
Yes, sir.
Okay.
Hello.
Is my screen visible to you?
Yes, sir.
Yes, sir. Sir.
Okay, fine. Please answer your attendance. Aditya Kumar.
Sir. Present, sir.
Okay, Anand.
Yes, sir.
Ananda Kumar.
Yes, sir.
Arnachalam.
Yes, sir.
Hasan. Hemant. Jagan.
Yes, sir.
Kesav Prasad. Lakshmi Narayanan. Prabhakaran.
Present, sir.
Prem Vinayak.
Present, sir.
Rahul.
Sir, Hemant also present. Sir, we are sitting in the M&M conference room, but few
Okay.
of there is some audio issue. So few of people telling attendance still you couldn't mark it. So I'll just open my laptop and then this one. Right now it's still Satish is clearing it by the time.
Okay.
So Hemant is present and Prem Vinayak also present.
Sir, Keshav is also present.
Lakshmi Narayan also with me, sir.
Kesav Prasad is present. Lakshmi
Yes, sir.
Narayanan is present. Lakshmi Narayanan.
He's with me, sir. Present, sir.
Hasan is absent, right?
Sir, I'm present today. I actually was traveling, so that's not joined, sir. Sorry for that, sir.
Okay. So you are attending the class, right? Hasan, you are attending the class, right?
Yes, sir. I'm attending the class, sir. I'm available, sir.
Okay. Rahul.
Yes, sir.
Roshan Kumar.
Yes, sir.
Sabish Kumar.
Yes, sir. Present.
Satish Kumar.
Present, sir.
Titus.
Present, sir.
Valish.
Yes, sir.
Vigneshwaran.
Present, sir.
Vijay
Yes, sir.
Vikas.
Present, sir.
Vivekanand.
Present, sir.
Yadav.
Present, sir.
Yuvraj.
Present, sir.
Okay. So all are present today. Okay, so welcome back. I have started this discussion on assignment 2 questions in the previous class. So I will continue with this. As I said, you please note down the solution procedure for answering these questions, and then submit it as an assignment. Complete this, complete answering these questions, assignment questions. Submit it as an assignment. Okay, the due date for submission is next week on Monday, not coming Monday, next Monday. This is what we decided in the last class. So I think I discussed question number 1 and 2, right? I have to now start with question number 3. Is that correct?
Yes, sir.
Yeah, question number 1 and 2 are theory questions. First question is about knocking tendency in SI engine. You are asked to comment whether it will increase or decrease. I mean, knocking tendency, whether it will increase or decrease in an SI engine with the following changes. So the changes indicated are in part A, the coolant temperature is increased from 30 to 80 degree. Okay, so whenever you are asked about knocking tendency in SI engine, you should relate it with the mechanism. You know, in SI engine, knocking is due to N-gas auto-ignition. Whatever variables given here, you should check from that perspective, whether it will increase N-gas temperature or not. You are actually increasing coolant temperature here. You should relate it with the condition of the N-gas because of this change, whether the N-gas temperature will be raised or lowered. Accordingly, you should say increase or decrease. Wedge-shaped combustion chamber with spark plug located at the center of the effective combustion space. So wedge-shaped combustion chamber, we already discussed in the combustion chamber type. That is one of the type of combustion chamber that we discussed based on the cylinder head shape. Okay, so this is generally used in V-type engine. You see here that the spark plug located at the effective combustion space. This is a space where the volume is more. So the flame has access to most of the charge in this region. And this is an N-gas region. So since the question is about knocking tendency, we should think about N-gas, whether this design will increase N-gas temperature or not, whether the flame will reach N-gas quickly or not. This is what you need to think to answer that question. The second question is about arranging the following 4 types of combustion chambers in the increasing order of knock producing tendency. So these 4 types of combustion chambers, as we know, it is based on the location of the valves, intake and exhaust valve. Based on the change in the location of intake and exhaust valves, you have these 4 types of combustion chambers. You have to arrange them in the increasing order of knock producing tendency, meaning the one that produces least knock should come in the beginning. The one that produces highest knock, right? One that has a highest knock producing tendency should come at the end. Other 2 will come in between. So it is like increasing order of knock producing tendency. First make the arrangement and then justify your arrangement with valid reason. Meaning you have to write the reasons why you have arranged so. You please mute your mic. I think there is someone has unmuted the mic. Could you please mute? I'm getting feedback noise. Okay, thank you. So now we are moving to question number 3. Question number 3, there's a simple problem, numerical problem. Okay, so I'll first read the problem and then discuss the solution. The spark plug is fired at 15 degree BTDC. BTDC is before top dead center. Always note that when we do combustion analysis, compression TDC is a reference point, right? Compression TDC is a reference point. Piston reaches TDC 2 times in an engine cycle in a 4-stroke engine. And our analysis is with respect to piston at the TDC point during the end of compression stroke. Okay. So here, spark plug is fired at 15 degree BTDC. What is this information?
It's 15 degree before TDC, sir. Like advance actually in that way.
So no, this information is the spark timing, right?
Right.
So timing of spark discharge is given as 15 degree BTDC in an SI engine running at 1500 RPM. This is the engine running speed. It takes 5 degree of engine rotation to start combustion. What is this information? 5 degree?
The crank angle time.
Ignition delay.
Ignition delay. More precisely, what is that called as? First stage of combustion, right? What is that called as? Flame
development phase.
Yes, flame development period. So you are firing at 15 degree BTDC. It takes 5 degree of the engine rotation, 5 degree crank angle. Time is taken to develop the flame. Okay, that is the time required to develop the flame. That is the first stage. Okay, and after 5 degree, the combustion gets started in the sense that the flame start to move from the spark plug and it start to propagate across the combustion chamber. So 5 degree crank angle rotation is the flame development time. After that, fully developed flame will start to move into the combustion chamber. So that's why it is given that after 5 degree rotation, combustion started and enter flame propagation mode. As soon as you discharge spark at 15 degree, technically the ignition will begin because it's a high voltage spark that you discharge. Ignition happens immediately. So there is no ignition lag or ignition delay technically. But what we are considering as a delay here is the time required to form a fully developed flame. The flame has to fully develop, otherwise the combustion event cannot sustain. It will start and stop. That's why this time delay is required. This is also called ignition lag, but technically there is no lag. As soon as you discharge spark, there is an ignition. Did you get what I'm saying?
Yes, sir.
So this time is required to create a fully developed flame. Okay. So after this time interval, the flame propagation mode is entered. Okay, the flame start to propagate across the combustion chamber. Flame termination occurs at 15 degree ATDC. What is ATDC? After top dead center. Okay, flame gets terminated 15 degree after top dead center. Okay, so until that point of time, flame moves inside the combustion chamber and ignite the mixture that present in the combustion chamber. Cylinder bore is present. Cylinder bore is 10.5 centimeter. This is the diameter of the cylinder. And the spark plug is located at the center of the cylinder. And the spark plug can be located either at the center or opposite. In this problem, it is given that it is located at the center of the cylinder, meaning along the axis of the cylinder. The flame front can be approximated as a sphere moving from the spark plug. So you can approximate the flame geometry as a spherical flame, and the flame front geometry is approximated as having a spherical geometry, and it moves from the spark plug location into the combustion chamber. Okay, this is the information given. With this information, you are asked to calculate the effective flame front speed during the flame propagation. The flame moves at some velocity. Okay, what is that velocity or speed is what is asked in the problem. The flame velocity may change, okay, with respect to time, but you are asked to find an average flame velocity, okay, during the period of flame propagation. After 5 degree time lag, the flame start to propagate across the combustion chamber at some velocity. What is that velocity or speed is what is asked. You are asked to find the effective flame front speed or flame velocity. That is the question asked in the first part of the problem. In the second part of the problem, the engine speed is increased to 3000 RPM. From 1500, the speed is double. It is increased to 3000 RPM. What will happen if you increase the engine speed?
The time, the crank angle is level 4. This thing is reduced.
Now, with respect to flame propagation, I'm asking what will happen if the speed is double?
Double the flame propagation, sir.
Flame propagation velocity will be high. Okay, velocity will be high because turbulence levels are increased when you run engine at a higher RPM compared to lower RPM. Okay, so because of the increase in speed, the flame speed is increased by 40%. By 40%. Okay, compared to the previous velocity, now the velocity is increased by 40% due to higher turbulence and higher swirl in the engine cylinder. Flame development after spark plug firing takes the same 5 degree of engine rotation. So for the case 2 also, the flame development period is the same 5 degree. So we are considering that the same 5 degree is taken for developing the flame, right? And then the flame moves at a higher velocity, which is 40% higher than the previous case. Now for case 2, you are asked to calculate how much spark timing must be advanced at 3000 RPM so that the flame termination occurs again at 15 degree ATDC. Did you understand what is asked in the second case? Flame termination again happens at the same 15° ATDC as the previous case. For case 2 also, flame termination happens at 15° ATDC after TDC. For developing flame, 5° is taken. After that, the flame start to move at a higher velocity. Okay, and flame termination is fixed at 15°. What you are asked to find here is how much spark timing must be advanced. Okay, how much spark timing must be advanced at 3000 RPM is what you have to find. If you don't advance the spark timing, what will happen to flame termination? When the engines instead of 1500 RPM,
it will move after like 15° will become maybe 30 or 40 after
yeah,
that.
Exactly. So at 1500 it is 15°. Now at 3000 also I want to keep this at 15°. If you since this is a constraint being imposed, okay, what will happen when the engine speed is increased? The crank angle covered in a unit time is increasing with increase in engine speed. So more angle will be covered in a given time. Okay, for case 2, since the engine speed is 3000, much higher than the previous case, okay, the flame termination will happen late if you don't change the spark timing. Did you get what I am saying? For the same spark timing, if at all it is 15°, like 15° BTDC, and if it is with 5° delay, that is for developing flame, then the flame termination will happen after 15°. It won't happen at 15°. Did you get what I am saying? Because the engine is spinning at higher RPM. Angle covered will be more, so it will move further ahead of 15°. As you rightly said, it may be 20 or 30 or whatever. Okay, but it happened at a later time because angle covered is more now due to increase in engine speed. We don't want that. What we want is the flame termination should again happen at the same 15°. So what you have to do? You have to advance the spark timing. Only by advancing spark timing, this is possible. Did you get?
Yes, sir. Yes, sir.
So for the second part of the question, you are asked to find that advance in the spark timing. For the first part of the problem, you are asked to find the flame speed. For case 2, you have to find how much the spark timing should be advanced at 3000 RPM so that the flame termination occurs again at the same 15° ATDC. So what I will do, I will write the data. So the information given to you are, one is, let us consider case 1. Information given are spark timing. This is equal to 15° before top dead center. Engine running speed is given 1500 RPM. Flame development period is given FDP. I'm writing this as FDP, which is flame development period. This is 5° crank angle. Flame termination, I have abbreviated is as FT, flame termination time. Flame termination time is 15° ATDC, which is after TDC, after top dead center. Cylinder bore is given. I'm writing it with capital D. Cylinder bore is 10.5 centimeter. Spark plug is at the center of the combustion chamber. So this is the axis. Spark plug is located here. Okay. It can be offset also in the given problem. It is mentioned that the spark plug is at the effective center of the combustion chamber. So here the flame is developed. From here it starts to move across the combustion chamber. The diameter or bore for the cylinder is given in the problem. Okay, and so with this information, this flame front is approximated as a sphere moving from the spark plug location. With this information, you are asked to find effective flame front speed. So this is speed, or you can say that flame velocity. So we have already discussed that the overall combustion event in SI engine is based on how the flame moves, because the rate of burning is dependent on the rate at which the flame moves. So flame velocity carries a lot of significance in SI engine combustion. Okay, that's why we need to find or track velocity of the flame, because this is going to decide the rate of burning of the mixture, fuel air mixture. Let us say this is VF1. This is what is asked in the problem, which you need to find. Now, to get velocity, go to the fundamental definition. What are the informations you need to have to get the velocity of the flame?
Slope of the curve, sir, in that way.
No. Go to the fundamental definition. Velocity. Velocity. How will you define?
We need distance and time, sir. So
Yes.
time from the crank angle from the end of, start of flame propagation to end, and then we
End.
also have the range.
Exactly. So we need velocity. We are going by the fundamental definition. So what information we need? Two information we need. One is distance traveled by the flame. During the flame propagation, what is the distance, maximum distance traveled by the flame, and what is the associated time taken? For traveling this distance, how much time is taken? These two fundamental information I need to have in order to get this unknown flame velocity. Now, how do I find the distance traveled by the flame? Based on the given information, what is the distance traveled by the flame? So when the flame develops, it is developing in the spark plug location. Here, there is a flame development. It takes 5 degree. It takes 5 degree crank angle time for developing the flame. Once it gets developed, it starts to propagate evenly, right, across the combustion chamber. Now, what will be the maximum distance moved by the flame, distance traveled by the flame?
So tangent of that sphere will be touching the piston top.
So can I say that it is d by 2? So it is moving evenly, okay, both sides. So max distance will then be d by 2, right?
Yes.
So max distance traveled by the flame in this case will be d divided by 2. Okay, so d is the bore, cylinder bore. Since the spark plug is located at the center, if the spark plug is offset, accordingly the distance travel, max distance will be different. Now in this case, the spark plug is at the center. So d by 2 will be the max distance covered by the flame, okay, on both sides. So this is distance travel, this is known information. How will you get the time taken? What do you have to, so please note that this is
theta is given, total
this
theta.
is the SI unit.
Vehicle speed, we have to convert theta.
Yes. So this is in meter, time taken should be in second. And the given information is spark timing is known to me. Spark timing is 15 degrees, right? Reference point is 0 degree, which is TDC, compression TDC. This is before, this is BTDC, which is before TDC in this direction. Right, so if you move in this direction, this is before TDC. In this direction, it is after TDC. This is my reference point. Okay, spark timing is 15 degree BTDC, before TDC. It takes 5 degree to develop the flame. Okay, so this duration is 5 degree crank angle, and this duration is flame development period. So this is flame development period, that is 5 degree crank angle. So what will be this angle then?
10 degrees, sir.
10 degree. So this is 10 degree. This is where the flame propagation starts. Now, when do the flame terminate? That is given in the problem. When do the flame terminate? This is 15 degree EA-TDC. This is 15 degree after TDC, the flame terminates. So this is a point of flame termination. So until this point of time, the flame is propagating at some velocity. This velocity is what you have to find. Okay, so now in this case, we know time in terms of angle, right? What is the total angle for flame propagation? For
25.
Flame propagation, what is the total angle taken? 25
degrees.
So that will be from here at this point of time to here At this point of time, it ends. It starts here, it ends here. So this is 25-degree crank angle. So this is a time in angle. You have to convert time in angle to time in seconds. We want time in seconds. Okay. So you know, in one revolution, the angle, what is the equivalent angle? 360-degree crank angle. How will you convert this angle into time in seconds? In one revolution, it is 360-degree.
RPM is given, sir.
RPM is given. So RPM, say if it is 1500 RPM, what is RPM actually? It is revolution per minute. So from this you know what is the angle covered in 1 second, right? You can always convert this. So angle covered in 1 second will be 1500. In one revolution, it is 360-degree. So this will be multiplied by 360 per minute is this time. So you have to divide it by 60 to get per second. So this will be the degree crank angle in 1 second. Did you get what I am saying?
Yes, sir. Yes, sir.
So this is a total angle in 1 second. So from this you can convert angle into second. Okay, so you need to do that conversion. Substitute here. You should be able to get VF1. This is for case 1. Case 2. Let us write the information given. For case 2, you are asked to find the spark advance. Is what is asked in the problem. The information given are flame velocity is 40% higher than VF1. What does that mean? 40% higher than VF1?
1.4 times.
Yes, this is 1.4 times of VF1. So this is known to me now, 1.4 times VF1, because VF1 you have obtained from the previous case. And other information given is it takes same 5 degree for flame development. So let us say this is a flame development period for case 2. This is again same as the previous one, 5 degree. And the flame termination for case 2 is again at 15 degree ATDC. Okay, so these are the informations given to me now. So this is in the time bar. This is flame termination for case 2. This is 0 degree, which is TDC. This is again 15 degree ATDC. Okay, and 5 degree is the flame development period for case 2. And what I don't know is ST, spark timing, for case 2 is unknown. This is what I need to find. This is 5 degree. This is known to me. Okay. Now, the flame propagation starts here, it ends here. So this period is a flame propagation period. Let us say this is FPP for case 2. Now, until otherwise you get this, you are not going to get this. Okay. How will you get flame propagation period for case 2?
Sir, I have got R, which is maximum distance that is going to travel. And I've got the flame velocity, propagation velocity.
This is known to me. Okay. This is known to me. This is equal to D by 2. This is not going to change, divided by time. So this is known, this is known. You can get time in seconds. Did you get what I am saying?
Right, sir.
Now you need to convert that into angle. Convert that into degree crank angle. So once you get this, so this information will be known to you in degree crank angle. Once you know this information, you can track this point. Once you track this point, you have to add to that this 5 degree. From that, you will be able to get the spark timing for case 2. And you can compare that with case 1 and say how much the spark timing is advanced. Clear?
Clear, sir.
Question number 4. So in question number 4, you are asked to write and briefly explain any 2 engine variables that influence the premix combustion phase and the diffusion combustion phase in CI engine. In CI engine, you know, there are 4 stages. First one is ignition delay, followed by premix combustion, followed by diffusion combustion. You are asked to identify and explain any 2 engine variables that affects premix combustion. You know, before premix combustion, you have the delay time. Any engine variable, already we discussed about the variable that affect ignition delay. Any engine variable that affects ignition delay is going to affect the premix combustion. Did you get what I am saying?
Yes, sir.
Yes, sir.
So what I mean to say here is we have, if you recollect the stages of combustion in CI engine, you have ignition delay followed by premix phase combustion, followed by diffusion phase combustion, followed by after burning. After burning generally will be ignored because it's a very slow phase that happens after the effective time period, combustion period. This is generally around 10 to 15% of the charge is burnt. 10 to 15% of the total charge will be burnt. Okay, so these 2 are important stages, and the duration or the intensity of these 2 stages are primarily dependent on ignition delay. Suppose if ignition delay time is longer, you will have more intense premix phase combustion, less diffusion phase combustion, because total fuel is injected fuel is fixed. Total fuel quantity is fixed. When most of the fuel is injected during delay time, because of a longer delay, you will have a more intense premix combustion, less diffusion combustion. Or vice versa. Suppose if the delay time is less, you have a shorter delay, less fuel injected during this period, premix phase will be less intense and diffusion will be more intense. So the premix and diffusion phase are primarily dependent on ignition delay. That's why we already discussed the variables that affect ignition delay. In this problem, you are asked to identify any 2 engine variables that affects premix phase combustion. So what you have to say here is any variable, any 2 variable you choose. You can choose a variable discussed in the class, or you can also choose any other variable other than what we have discussed. So you discuss how that variable affect delay time, and then relate that with the premix phase combustion. If the delay time is increased or decreased, accordingly premix phase will be more intense or less intense. Did you get what I am saying?
Yes, yes.
Okay, so that's what you have to do here for the question number 4. You identify engine variable. It can be design or operating variable. You say how it affects delay time, and through delay time it affects premix combustion. The second question is about, the part B is about how it affects, how the variables affect diffusion phase combustion. Diffusion phase combustion, as we discussed, it's a slow burn phase, right? And this phase is primarily governed by the mixing, rate of mixing, fuel air mixing. So any engine variable that affects fuel air mixing is going to affect the diffusion phase combustion. Okay, any variable, engine variable, it can be design or operating variable that affects the mixing. Basically, the rate at which the diffusion phase combustion happens is primarily based on the mixing, fuel air mixing. Okay, so it means any variable that affects fuel air mixing is going to affect the diffusion phase combustion. Clear? The next question is about draw and comment on the heat release rate profiles of a CI engine operating at idle. Idle is no load, right? When you start your vehicle, it is in idle condition. Until otherwise the vehicle moves, the brake power is 0, right? When the vehicle is at rest, brake power is 0. That is idle condition or no load condition, because brake power is 0 at this condition. And full load condition. Full load is the rated power condition. You are asked to draw and comment on the profile, heat release rate profile for a CI engine under these 2 conditions. One is no load condition, the other one is full load condition. What will be different in these 2 conditions?
The peak pressure will be different, sir.
Peak pressure will be different. So this is a heat release profile for a CI engine. You are asked to draw this heat release profile, heat release rate profile for no load condition and full load condition. What will happen to the ignition delay time at no load and full load?
Sir, ignition delay time will be more in, I would say, in the no load condition compared to the full load condition, because
Okay.
conditions are favorable for lesser delay time in the full load condition.
Okay. So here, so you should first check what will happen to delay, which is the first stage of combustion. first stage of combustion, what will happen to delay time at no load and full load? These two are the conditions given, right? So no load, the duration of delay time, it depends on the in-cylinder pressure and temperature condition. What will be the pressure and temperature? Let us say this is P1 and T1, and this one is P2 and T2. In a relative sense, what will be the pressure and temperature value at no load and full load?
P1, T1 will be lesser than P2, T2.
So this will be lesser, this will be more. This is no load, you burn less fuel, so in-cylinder pressure temperature are lower. At full load, you burn more fuel, in-cylinder pressure and temperature will be high. So in a relative sense, this pressure and temperature at the time of fuel spray. So basically, when you spray fuel into the engine cylinder, the in-cylinder conditions we are taking as APT. I'm talking about these conditions, right? Here I have indicated that as P1, T1 and P2, T2 at the time of fuel injection. When in-cylinder pressure and temperature are higher, the delay time is going to be shorter. Okay, because overall delay time is physical delay and chemical delay. Chemical delay is based on composition. It is also sensitive to temperature. Physical delay is based on how quickly you get this ignitable mixture. Okay, all this depends on in-cylinder pressure temperature condition. When the pressure and temperature are high, you're going to get a shorter delay, overall delay, because there is a shorter premix, there is a shorter physical delay and there is a shorter chemical delay. Overall delay time will come down when pressure and temperature are high. Opposite is true. Suppose if the pressure and temperature are lower, suppose if the pressure and temperature are lower at the time of fuel spray, then you will encounter a longer delay because pre-mixed, in the overall ignition delay time, the physical delay time will increase, chemical delay time will also increase because the temperatures are reduced at the time of fuel injection with at no load condition. So you will have a change in ignition delay time based on in-cylinder pressure temperature conditions at the time of fuel injection. In-cylinder pressure temperature conditions at the time of fuel injection is a strong function of the load, engine operating load. So this will be the status of pressure temperature or in-cylinder conditions at the time of fuel injections in these two load cases. Now, when the ignition delay at no load, when the ignition delay time is longer, just now I said that you're going to have a more intense premix. Okay, so when this is high, this is going to be more intense and diffusion phase is going to be less intense. When ignition delay is shorter, premix phase will be less intense and diffusion phase will be more intense. This you have to show it in the heat release rate profile. Okay, is it clear? So this is at no load. This is at full load. Is it clear?
Yes, sir.
Clear, sir. Clear, sir.
Okay. Question number 6, comment on the ignition delay, increase or decrease in a typical CA engine with the following changes. Fuel injection timing varied from 10 to 30 degree B TDC before top dead center. Piston bowl shape is modified from flat geometry to deep toroidal. So there are two parts of this question. One is change in injection timing. So you have two different injection timings. One is 30 degree. Let us say this is TDC point. This is 30 degree before TDC. The other one is 10 degree before TDC. So you are injecting fuel, right, at 30 degree instead of 10 degree. The question is about comment on the ignition delay when the fuel injection timing is varied from 10 to 30 degree. Right, so if you move from 10 degree to 30 degree, what will happen to the ignition delay time? This is a question whether the delay time will increase or decrease. Again, this depends on in-cylinder conditions. So you have one condition here, let us say P2, T2, and this is initial condition, let us say P1, T1. If you move from here to here, you should think about the in-cylinder conditions. Accordingly, the delay time will increase or decrease. The second question, the second part of the same question, you are asked to comment on ignition delay when the piston bowl shape is modified from flat geometry to deep toroidal geometry. So case 1, you have a flat piston like this. Case 2, you have a deep toroidal piston. So this is deep toroidal piston, resembles letter omega. I mean symbol omega. Okay, so this is flat. This is deep toroidal. You need to comment on what will happen to the delay time, ignition delay time, okay, because of change in the bowl shape from this to this. So what will change if you move from flat to deep toroidal? What effect it will have?
It will increase the turbulence, mixing.
Mixing. Okay, so here you will be able to generate some squish because of the piston upward movement, but there is no swirl because the piston is flat. In the second case, you are going to create a squeeze, and then you are also creating a swirl because of the piston shape. So mixing, fuel air mixing is going to be different in these two cases. Now you have to relate that with the ignition delay time. Right? You have to comment on if I move from this to this, what will happen to the ignition delay time, whether it will increase or decrease. The last question, arrange the following CI engine combustion chambers in the increasing order of squeeze producing tendency. Squeeze producing tendency. Squeeze is a radial motion. Okay, so you have 3 different combustion chambers: hemispherical, shallow bowl, and deep toroidal. This is hemispherical, this is shallow bowl, this is deep toroidal. You have to arrange these 3 combustion chamber in the increasing order of squeeze producing tendency, meaning the one that produces least squeeze should come in the beginning. The one that produces more intense squeeze should come at the end. Okay, so you have to arrange them in an order of increasing squeeze producing tendency, and you have to comment on your arrangement. Why you have arranged like that, you have to comment on. Suppose if you say that a particular design increase squeeze, you have to justify that why it increases squeeze. Clear? Any questions? Are there any doubts?
No, sir.
Okay, there are no doubts, so I will move ahead. So I assume that you got the answer, solution key for this question. So complete it as an assignment and submit it to me by next Monday, on or before next Monday.
Yeah. 1st of April, sir.
What is it?
1st of April, sir.
Yes, 1st of April. Okay, so now.
Sir, just one question for the quiz 2. The portion will be chapter 3 and 4, right? Sir, if I'm not wrong, what you have told.
Only chapter 3. Quiz 2 you are asking?
Quiz 2, yes, sir. Yes, sir.
Quiz 2, I didn't say anything about this level. What I said is whatever we are going to discuss before the exam will be the syllabus for quiz 2.
Right, sir. Thank you, sir.
I think we should be able to complete chapter 4 also, maybe chapter 3 and 4, but I will just confirm. So your exam is on Saturday, right?
Yes, sir. This Saturday we have the exam, and
Yes, sir.
ours is on 5th April, if I'm not wrong.
That is next Saturday.
No, sir. 15 days after, sir.
15 days. So I think we should be able to complete this. Okay.
Okay.
So you may have to go through these 2 chapters. If there is any change, I will inform. I will confirm the syllabus anyway, well before the exam.
Thank you, sir.
Thank you, sir.
Okay. So now we are moving to chapter 4. Chapter 3 on combustion is concluded. SI and CI engine combustion, we have now understood how the combustion event happens in a spark ignited engine and compression ignited engine. The next chapter is about instrumentation to study the combustion process in engine. Having understood the process, combustion process, okay, so we need to know how to analyze this process in a given engine, SI or CI engine. To analyze the process, we need data, right? So we analyze the process using data. It is called quantifying the combustion process. To quantify the process, we need to do measurement and acquire the data. So we need to get familiar with what kind of instruments and what type of working principle is involved to get the basic combustion data. So I will start with the instruments that you need to have to acquire the basic combustion data. The basic data record is the pressure profile. Pressure profile is that will show how the pressure inside the cylinder vary with respect to crank angle. Okay, that is a basic or fundamental data that you need to have to analyze the combustion event, okay, or to quantify the combustion event in SI and CA engine. You need to have a pressure profile. Now, once you have a pressure profile, you will be able to derive other parameters by using this profile. So there is a measured data, which is a pressure profile. By using this measured data, I will show you how you can obtain other useful combustion parameters. Those are called derived parameter because basically all these parameters are derived from the measured pressure crank angle data. Once you have this, I already said that this pressure profile is called cardiograph of an engine, like how ECG shows our heart functions, how an engine functions is given by the pressure profile. It is said to be the cardiograph of an IC engine. Suppose if there is a knock or normal combustion, just by looking at the profile, you can say this is a normal combustion, this is abnormal or right knocking kind of combustion, just by looking at the profile. Okay, this is one of the important information, critical information, as well as this is one of the fundamental information that you need to have to analyze the combustion event. So in this chapter, we are going to discuss about the measurement principle followed to get the cylinder pressure, what instrument we use and what is the measurement principle followed. Similarly, we will discuss what instrument we use to measure crank angle and what is the measurement principle followed. With that information, I will also talk about how we can get other parameters, derived parameters by using this pressure and crank angle. And that will help you to analyze the combustion event in IC engine, both SI engine and CA engine. So as said, the fundamental data required to analyze the combustion event is one is instantaneous cylinder pressure and the other one is instantaneous crank angle. What do you mean by instantaneous pressure and instantaneous angle?
At that particular crank angle, basically, at that instant, actually.
At the instant, time instant, right? So this is at a particular time instant. So we are talking about the pressure that we measure inside the cylinder at a particular time instant. And we are talking about the angle theta measured. Theta is the crankshaft angular position. Angle measured at a particular time instant. That is what I mean by instantaneous angle. This is instantaneous pressure. Apart from this, you also need an important information, which is compression TDC position. When you say angle, you are counting that angle. To count the angle, you need a reference point. The reference point is always compression TDC position, right? Why I am saying this as compression TDC, not simply TDC. In a four-stroke cycle, you know, piston reaches TDC twice. One during end of compression, other one during end of exhaust. End of exhaust, we are not bothered because that is not the period where the combustion happens. The combustion happens when the piston is at TDC at the end of compression. Around that period only the combustion event is happening. That's why we take this as a reference point and measure angle with this as a reference point. Okay, so this three information you need to get precisely. Okay, and from this you are actually obtaining this pressure profile. This is one of the most useful or critical information that you need to have to analyze the combustion event. Instantaneous cylinder gas pressure, instantaneous angle, and this angle is reference with respect to compression TDC position. So the other important information here is we are analyzing cylinder pressure in a crank angle domain, not in time domain. What do I mean by that? This is crank angle domain. This is time domain. Absolute time in absolute time unit. So we never analyze pressure with respect to pressure variation with respect to absolute time, which is time domain. We always analyze pressure variation with respect to crank angle variation. Why it is so?
You have told us that because combustion is phased with respect to TDC.
Yes.
in angle manner. So if the RPM increases, there is no relevance of time in that way.
Yes, so this is meaningless. If you analyze in-cylinder gas pressure variation in a time domain, right, with respect to a particular time, if you analyze how the in-cylinder gas pressure varies, this doesn't make any sense at all. This makes a lot of sense because when you analyze pressure with angle, this angle, whatever you are saying, crankshaft angular position is related to the instantaneous piston position. These two are interrelated by slider crank relation because the engine that we use are reciprocating engines, not rotary engines. These are reciprocating engines. IC engines, whatever we use currently, they are not rotary. Rotary engines have very limited application. Wankel engine is a rotary engine. It has very limited application. It's a failure design. Right? This is what we use in a reciprocating engine for any instantaneous crank angle. There is an associated piston position. Okay, so piston moves linearly up and down motion, and crank moves undergoes rotational motion. These two are related through slider crank relation. Okay, meaning if I relate pressure with angle, I am relating this angle can be related to piston position, linear piston position. Meaning I am analyzing how this gas pressure varies in the cylinder with respect to the position of the piston in the cylinder. Okay, when I analyze in P theta domain, I am analyzing how the pressure varies in the cylinder with respect to position of the piston. So this gives me information about the piston position. So when I say the pressure value is this much, this is related with the piston position. This makes a lot of sense because, you know, ideally at the start of expansion stroke, we want maximum pressure in the cylinder so that you can extract maximum work from the gas. Expansion stroke is the only stroke where work is done by the gas. It's a positive work. During rest of the time, the piston provides work to the working fluid. Okay, it's a negative work. Only during expansion, it's a positive work. So we are analyzing pressure variation with respect to piston position. This makes a lot of sense, and with theta, crankshaft angular position, you can always relate that to the linear position of the piston by slider crank relation shown here. Y theta is the instantaneous piston position is equal to L plus A minus S. What is L? L is the length of the connecting rod, and A is the crank arm length. A, this is L, and this is S. Okay, the S is connecting. S is the distance from here to here. Here to here is S. Okay. And this is L, connecting rod length, and A is a crank arm length. Y theta is any position. This is Y theta. Any linear or instantaneous position of the piston is Y theta that can be obtained from L plus A minus S. What will be the value of S when the piston is at TDC?
L plus A, sir.
At TDC, S will be L plus A. So Y theta will be 0. Okay, when the piston start to move down, S will decrease from L plus A. Did you get what I am saying? When the piston starts moving down or moving up, okay, it cannot move up. That is a dead center. When it starts moving down from TDC, okay, S will decrease from L plus A. The decrease in S from L plus A is a measure of Y. That is the instantaneous piston position. Did you get what I am saying? So that's why this relation relates a linear position of the piston with respect to S, and S can be related to angle, crankshaft angle. This S, this distance from here to here can be obtained from this triangle. This distance will be summation of this and this. This distance will be A cos theta, and this distance will be L square minus A square sine square theta square root. Okay, L square minus this is A sine theta. L square minus A square sine square theta square root. That is what is this distance. This distance plus this distance will give you S. Okay, so through S, you are relating S with the theta, crankshaft angular position. From that, you are getting instantaneous piston position Y theta. And from this, you can get the instantaneous volume. V theta is the volume occupied by the piston inside the cylinder at any linear position Y theta. That will be given by VC, which is clearance volume. This is a volume when the piston is at TDC. And this is the additional volume that you get based on the piston motion. That is cross-sectional area pi d square by 4 multiplied by y theta. Okay, this is the instantaneous volume in the cylinder at any linear position of the piston y theta. And y theta is related to L plus A minus S, and S is related to the angle theta, which is a crankshaft angular position. This is slider crank relation. Since we deal with reciprocating engine, right, this slider crank relation relates the crankshaft angular position with the linear position of the piston. That's why when I say that I am analyzing pressure variation in the angle domain, I am analyzing pressure variation with respect to piston position inside the cylinder. That's why this makes a lot of sense in combustion analysis. So the fundamental data you need to acquire are cylinder pressure at any point of time in angle domain, instantaneous angle, then compression TDC. With this three information, you'll be able to get this profile. Once you get the profile, you'll be able to derive all other parameters, combustion parameter from this information. I will talk about that in the next class. First, I will talk about how we can get pressure measurement done and instantaneous angle measurement done, how we can get compression TDC. After that, I will talk about how we can derive other parameters from the pressure profile. I stop here, it's time up. If you have any questions, I can take. Are there any questions? Okay.
So regarding the assignment that you have told us to submit by 1st of April.
Yeah. Yes.
The theoretical question that has been asked, basically, as you have been saying that the only like what I mean to say conceptual lines, which are the gist of thoughts that we are willing to like express. That is more than enough. No vast answer and something like that.
Yeah, descriptive answers are not required for exam as well as for assignment. You can make it very brief. What I will check is I will check whether you understood the concept or not. You can convey that in a very brief manner.
Thank you, sir.
Okay. Okay, I stop here. I'll see you on Monday. Thank you.
Thank you, sir.
Yeah, thank you.
Thank you, sir.